Okay, guys online, can you hear me?
Yes.
Yeah.
Awesome. Cool. Thanks, guys. So let's jump into it. First things first. A couple questions about Piazza. I forgot to make Piazza board last night. I apologize. That'll be on the top of my list of things to do tomorrow morning. If you have questions, I'm going to break my own rule. Feel free to email me for the next 12 hours or so, because I probably won't get to it tonight. So expect a Piazza board by this time tomorrow, hopefully tomorrow morning. If you have a question for tonight, go ahead and just email me. Other logistic stuff. That first quiz was out. Actually, the responses and answers were pretty good. Most everybody got everything right. There were a couple things that were a little off. Remember that the functional programming question got some people. I think that was pretty obvious once you answered it. Scala is the language we'll learn, but paradigm, and that's an important word we'll talk about a lot. The paradigm we're learning in is functional programming, not the language. It's a paradigm. Similar ideas, but very different. The other question, I think some people got confused between what syntax and semantics are. We'll talk about that a bit more today. But remember, syntax, that's your symbols in the language, that just think the characters that you type out. And the semantics are, how do you interpret it? What's the value of the program when you run it, for instance? So I think that's it as far as recapping from yesterday that I want to do, because we didn't cover a whole lot. Any other questions, though, before we get started? I'll usually start that way, asking if you guys have any questions. So, yeah, so there's a question, when's the first assignment due? It'll be assigned on Monday, and it'll probably be due on Thursday before class. It'll just be a 2-day assignment. It'll be shorter. It won't be a very long one. Like I mentioned before, for the first 2 weeks, which is not really this week, it'll be week 2 and 3, you'll have 2 assignments instead of just 1. So have that on your radar. And then a little bit of a disclaimer on using the recordings of the class. Just make note, we are synchronous. So if you're not in lecture and the thing doesn't record, I will not make a lecture recording after if it goofs up or something. We are supposed to be synchronous. The recordings are there in case you do accidentally miss class or something comes up. But there's a chance something goes wrong on my end. I forget to hit record, or I don't upload right away. So just make sure you're attending class if you can, because there might be some outages per se otherwise. I think that's all I wanted to hit before class starts. I don't see any other questions, so let's jump into it. So yesterday and remind me if I'm wrong, we finished off, I was defining the Boolean types, right? I think that sounds right. We were talking about Booleans. So we'll start with just a recap of that. So defining Booleans. We did this by first, writing our fancy B. Ooh, that could be interesting. Hopefully my pencil doesn't die. And remember, this symbol means it's the definition of equality, right? We're saying this thing Boolean is defined as. And it's defined as either true or it's defined as false. Or the Booleans as a set are true and false, right? A separate question, we'll elaborate on this in a second. This is kind of a silly question. How many elements are in this type? 2. I'm getting a lot of people are raising their hands for those of you online. 2, there's 2 of these. Okay. Simple question now. This will become a little bit more of an elaborate one when we start playing with larger data types. Just something I want to point out. Have you thinking about the size of things as we go on. Can we do anything interesting with the Booleans? Like just as I've written them down here, just with this definition, can we do anything interesting with that? Yeah. Say that again?
Binary count? A 0 and 1.
You can't quite do counters yet, which is a good point. We'll get to that in a second. Can we do anything else interesting with just the Booleans? Or say I give you maybe 2 Booleans. Can you compute anything with Booleans? See, anyone have any thoughts online? Yeah.
Truth tables?
You could do truth tables, right? When we calculate truth tables, what kind of operations do we usually talk about?
Comparison.
Yeah, comparisons. So what are the comparison operators you're thinking of?
Oh, the and or.
And or are the big ones. You also have NAND, right? Not and. You have XOR, things like that, right? You also have not. Okay, so we call these comparisons, we actually call them functions, or they are functions, right? So they take in 2 Booleans and they give you a new one, right? If you think about it in kind of the function style. So this is kind of getting us more into the semantic domain now. We're saying, what can you do with these Booleans? So far, I've just written some Booleans. I've just told you what they are. Now let's talk about what we can do with them. So we're going to usually write functions in a certain style. And so I'll do an example, then abstract. So let's start by just writing the not function or negation, right? So I can write not. And then any time in this class we define a function, I'm always going to give it a type. Okay, so we're going to talk about the type of the type of a function a lot. So think of this as your function signature or your method signature, right? So not, and we write has type. I think that should be similar as yesterday when we were talking about true and false having a type. Same here. So not has the type Boolean to Boolean. So it takes a Boolean and returns a Boolean. So the arrow can be read, I'll use the lighter purple. So for instance, A arrow B. A function that takes an A and returns a B. This is notation we'll see a lot, okay? So now let's continue defining this function. So whenever we define a function, we first give it that type, and then we actually define what it does. So for not of true equals what? False, right? So not true is false, and not false is true, right? Okay, so we're just kind of flipping them around. You guys are probably used to seeing functions written with parentheses around the arguments. We could do that, but it would get really old really fast. So in this class, we're going to remove the parentheses, okay? Just leave them, we'll space everything out so it's nice and readable. When you start programming in Scala, you'll use parentheses, but for in class, I'll probably leave them off, mostly because it's what I'm used to. It's what, at a higher level, what we do. We just leave it off. So I will put a note there though. You can kind of also write it like that. So now if I wanted to compute something with this, I could actually if I'm thinking about programming, I could call this function, right? And I could in a program do something like not true, and I could run that program. If I ran that program, what would it give me?
False.
It would give me false, right? Okay, why does it give me false? This is a little pedantic, it's supposed to be. It gives me false because I defined it up here, right? I told it anytime I give not a true, it becomes a false, okay? This is the beauty of what functions are. They're really simple. There's not a whole lot going on. You just say, you know, when I have this thing, it becomes this new thing, okay? It's just kind of mappings, right? What else to point out about that? Could we write and or an exclusive or in a similar style?
Yeah, but you probably need more than one. You need more than one thing you're passing to the parameter.
Yeah, more than one thing you're passing in, more than one argument, right? More than one parameter. All those words are the same. We'll use that language. We'll get really comfortable with using the language of functions pretty quick. It'll take some time. No worries not having the word for it on top of your head. Yeah, so let's start with and. Can we define and? Pose this as a question. Okay. How should we get started? What's the first thing? I just told you guys, what's the first thing we always do when we start writing a function? We give it a type, a signature. So whenever we're writing a function, we always give it a type or a signature first. So we say and has type. Okay, what type does it have? What does it return? Let's start from the back. What's the result of and? Don't overthink it. A bool. Right now, all we have are bools, so we can only use bool here. So at the end, we end up with a boolean. Now, what do we pass into it? 2 booleans, right? So this is going to take some mental gymnastics. I never told you how to write more than one argument, right? What's the type of a function that takes more than one argument? Well, we just string together arrows. It's pretty simple. So how we write that is takes a bool, arrow, bool, arrow, bool. So it says here, switch to commentary, takes 2 booleans as arguments. And it returns a bool. Now we'll get to why I wrote it like that in a second. There's a really, really good reason. It's really good. It's one of the cooler things about functional programming when you finally intuit this. But we'll get back to that. So let's define and now. So the actual function part, not the type of the function. So what cases do I need to cover? So up above, I had 2 cases, right? A case for true and a case for false. In and, how many cases are there? We'll say at most there are 4, right? So let's write those 4 cases out. Give me a case.
0, 0.
So 0, 0, false and false. I'll stick to using the full language, so bear with me for that. It's not going to be super fun to write, but there's a reason for it. And what's that? False, right? So that's how we write that function. Or the first clause or the first kind of case, right? So we're talking about cases, clauses. Those will be kind of similar kind of terms. What's another one?
True and false.
So we have true and false. And what does that give us? False. Okay. How about our third case? And what does that give us? Also false. It's a pretty boring function so far, right? And then our last case, I'm going to guess is true and true, right? What's true and true? True, right? Okay, so you're like, Jack, why are you putting us through this headache? This is really boring. Mostly just get you guys familiar with syntax here. But also to point out, we're just defining these functions by cases, okay? You could also write an if then else in a traditional programming language. That's probably what you would do. You could also use a switch statement. That would work great too. In Scala, you'll use something called a case expression, but it's all the same thing. You're just testing different possible branches. The first thing I notice about this function, or actually, yes, I'll get to that in a second because there's some questions online. So would it not be, the type of this not be B comma B arrow B? Why not that? Why not that?
That's not part of our syntax, having two inputs.
I haven't introduced it yet. That's a good point. We will introduce that notation. We won't use it very often. So there's a little bit of a difference between the arrow notation and using those commas. We'll explain it later. Just know there's a difference. For now, it's not super important. If you wrote this, I wouldn't probably take points off, maybe, but do the arrow notation. It's better. And I think actually someone maybe pointed. Yeah, so Brian asks, does the arrow notation we used above up here, does that mean that it's actually a function that's a composition of two functions that take a single input? You're using not the right language, but the idea that you're getting at is 100% true. So when I defined our syntax up here for these types, I said A arrow B. I said nothing about how you nest those. This is a type. So if that's a type, could I shove a function in the A or the B? Why not, right? So all this is actually in the B spot, I've put another function, okay? Which means, okay, well, if I give and a Boolean, so if I do and true, what does that equal? If I just do and true, I don't give it a second argument. What do we get? Do I get a Boolean back? What kind of thing did I just compute? So let's look at it this way. I'm gonna put some parens up in our definition above. When I put parentheses there, forget everything in the green right now. I've given this function a B. What does it return now? Yes?
A function that asks for another parameter?
Yeah, so it actually returns a function like in the meantime. And that function expects another parameter. So and true now has type bool to bool, and it's a function. So I could say and true equals, I'm gonna abuse our notation a little bit here. If, or actually, nah, I won't. And true, and I could just write, I could forget the false branch that we had before. So I kind of can forget some of the stuff that we had in the definition above. I'm partially computing, partially applying. We call this partial application. We'll talk about this more later. It won't matter a whole lot the first few weeks, but it explains why the arrow notation is so great. It allows us to partially apply functions. You're like, why would we ever do that, Jack? Take my word for it, it'll matter a lot later. It's going to be a actually one of the best tools of functional programming is this partial application notion. It lets us do a lot of really, really cool stuff. Sweet, perfect. Brian, great comments in the chat. I think you were a step ahead of me as I was going, so that's awesome. What else do I want to remark on this? We've defined and. Okay, what do we notice about and? So I have 4 cases here. Now I have a new question for you. Can we make this definition with only 2 cases? What do we think?
If we use the not part as well, then we could say if it's both true and if it's not that.
So we can't use not that way. I like how you're thinking though. We can't do that, at least in the type theory that we're using. That's actually a really, I haven't ever had someone give that response before, but that's actually a really advanced area where it's called pattern, what's the word I'm looking for? Pattern synonyms, I believe. It's a different construct, but you could do that, just not here. We're not going to use that notion yet. But you can do it in 2 cases. You're thinking along the right lines, sort of. So when we want to reduce the number of cases in a function, let's look for patterns, similarities. What's the similarities in and? Do any of the cases have like a similar pattern? What's the pattern?
Yeah, if it has a false, then it's going to be false.
If it has any falses anywhere, it's going to be false. What happens if you kind of negate that statement you just made? What's the other way of saying that?
It's both true.
Then it's true. So let's start with that case, right? Because that's the interesting case here. So we have and, I've already given it a type, so we'll skip that part. So and true is true, right? Now, if there's a false in it, I can just make it false. How do I write that though? How do I really concisely write this false case? What could I introduce? This is new notation. Looking for a V word. Yeah, so a couple people online are saying you could have an otherwise case. You could have a default output and have that be the false case. Both of those answers are on the right track. I like the otherwise answer for Brian a little better. But I think you guys are both hitting on the same idea. So here I could have basically in all other cases do false, right? And how I write that, and I can write this 2 different ways. I could give variables. That's the V word I was looking for. I can also use variables when I start to write a function like this. I don't necessarily need my arguments to a function to be anything specific. They could just be general, right? When we go on to find, I think, or next, we'll actually make really good use of this. And so here it just says for any X and any Y, I'll actually write that. That's not how you write any. They are then false. Okay, now doesn't that also include the true case? That's kind of a hiccup, right? How do we get around that? Well, we always read top down when we write these definitions. So always try and match on the first one, and if it doesn't match, then you go down the list, okay? So make a note on that. Read the cases in a top-down manner. A lot of this is still just kind of convention. We're just getting used to writing functions. So Another way I could write this that is equivalent is instead of putting X and Y, I don't use X and Y in this function. So I could also write and I could use an underscore, basically using that as a wildcard. 2 underscores equals false. We might encounter this. I'm not sure if I'll actually use that notation a whole lot, but just in case I do, it means the same thing. And these are really unused variables. It's just kind of how to write these things concisely. So who's bored yet with these like really simple functions? Pretty boring, right? I'm going to bore you a little bit more before we get to the fun stuff, just to get some practice in, because we'll be writing these a lot. We'll just get more interesting, so we'll have more fun as it goes. Let's write the OR function now. How do I write the OR function? This is, or actually I'm going to save that because that might be under your recitation. So I won't do that one yet. Similar style though. What else do I want to remark on here? Are there any questions so far? Everything making sense? Is anyone super lost? Cool. We're starting off slow. So we can, oh, okay, I saw that question. Sorry, Arthur.
It says, wait, so each of these is not just assigning the value.
So yeah, so sorry. Wait, so each of these is not just assigning a value to an out variable, but explicitly activating a return statement. So using the language of return statements isn't quite right here, because for instance, in the case of that partial application, we're not really returning anything per se. But it's more saying, well, it is. So actually, I would say it is just assigning a value to some set of inputs, right? So it's an assignment of inputs to outputs. Is all we're doing here. To say it's returning anything isn't quite right, because we're not allowed to do like variable assignment or anything like that. We're always saying this, when computed under this function, returns something new. It's never going to make some state change and not return anything, for instance. Does that answer your question, Arthur? Or could you elaborate if I didn't quite hit it? Okay. Maybe typing, so I'll give him a second. But I will start to write the header of our next section. So kind of moving on, the Booleans aren't super interesting to compute with. We can define 4 different kind of like early functions on them. You have an identity function where you just map the input to the output. It's the same thing. If I give you a true, it outputs true. If I give you false, it outputs false, right? I could define a constant function. So constant for true. So if I give you a true or a false, it gives you true. If I give you false, it gives you, or if I give you false or true, it also just gives you false. Or I could define not. That's it. For functions that take 2 arguments, there's a few more of those. There's actually quite a few more of those. Before I touch on that though, I'm going to finish answering Arthur's question. So yeah, so Arthur says if he's understanding properly, that means every line of code is in a sense returning something. Yes, it is. And that's a good observation. Sometimes it won't be every line, but every case will. So later we'll see situations where maybe the case just for formatting reasons is more than 1 line long, but you can always write these things as a single line if you wanted to, I would think. Otherwise, it's just a syntax thing. So you could always kind of collapse it to a single line. That's a good question. So thanks for fitting me down to that. So how many how many terms have type bool to bool? And we were just talking about this. The answer is 4. ID const true, const false, and not. Now, you don't necessarily need to know what these do. Just know that there are 4, okay? Now, my next question is, how many are in the bool to bool to bool type? Any ideas? This might be a question you guys had in an earlier class, but yes.
Yes, but like potentially like 4 factorial.
Not factorial. You're thinking in the right domain though. It is big explosion, but not quite that big. How many of those are there? So there's 2 arguments, right? And so how many different ways are there of making 2 arguments happen, right? So if you have 2 pairs, there's 4 different ways. There's true, 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 false, false, true, and false, false. How many different outputs could you assign to those, like uniquely assigned to those inputs? So 4, why do you say 4? Oh, so for a given function, there's 4, right? But what about just how many total are there? Sounds like it's a big number. There's not actually that many ways, 16. So there are 16 of these binary operations on Booleans. Now, how did I know that? So I'll start this with doing it on the first one. So we have 2 possible values for Boolean up here, right? And 2 in the output, okay? With me so far? This becomes 2 to the 2 when I'm working on arrows. So an arrow produces 2 to the 2. So that's 4. Now, which one do you put in which position? We'll get to that in a second. So now when I'm doing B to B to B, I have 2, 2, and 2, right? How many ways are there of making that? There's 4, right? Just like up here. Now, how many ways are there of making something that's, so I have 2 and 4. Do I raise 2 to the 4 or 4 to the 2? It is 4 to the 2. They're both 16 though. So that's a good, yeah, this is a bad differentiator, but it's 4 to the 2. So you always take 4, which gets us 16 possible functions. Have that type. So when I have something, I'll use a different color for this. When I have A arrow B, and I'm going to use these magnitude bars for the size. Is B raised to the A. Okay. This might be useful on your quiz tonight. Hopefully, I think I wrote that question. So. Okay. We know the size of this is 2. Later, it'll be a little harder to define the size of data types. We'll get to that later. Let's see, how are we doing on time? We have 40 minutes still. 80-minute classes are a long thing, so. Sweet. Yeah, so with that done, let's move on to defining a more interesting data type. I think what we're gonna do is I haven't done this before, but we're gonna do something new today that I haven't done before. How could I define bytes? So like 8 booleans, right? So if I wanted to define bytes, 8 or 4, 8. What's 4 called? There's a word for that. No, bit's 1. Oh, or is it? I don't remember. Does anyone? Oh, is that just a short? Thanks, Ronak. That I think it is just a short, or maybe yeah, because it goes up to 256, right? And 4 would represent. No, 4 would represent. This shouldn't be that hard. 256 would be.
I think 4 is short.
Would be 8. Yeah, 4 is short. That sounds right. It's a good thing we aren't in like an operating systems class or something, because that would get us into trouble. Anyway, so how do we define, say, a byte where we have 8? How could we do that? So we want to define a new type. Or actually, I'll pose the question first in the notes. We define bytes. So when we define a new type, we always use the same syntax, right? So I have byte, and I'm defining byte to be. What goes here? What is a byte? Can anyone tell me? Oh, thank you. It's a nibble. Is 4 bits.
That was a joke.
It's a nibble, and I think it is more of a joke because I don't know how often you use 4, but that's funny. What is a short now? Now I'm
I
confused.
still think short's 4, but like.
Is a short? Those might be the same thing. If anyone can online can look that up, I'm very curious now. But anyway, so how do we define byte? What is a byte? We've said it a few times. Someone just regurgitated it for me. It's 8 bits. Okay, so if we're representing bits by the Boolean type, how do I write 8 of them? Okay, so I'm going to write. This is going to be a little confusing at first. I'll use a lowercase letter to make this more clear. So we have a byte, not a but, a byte. And a byte is Boolean, a Boolean, Boolean, a Boolean. There's spaces between these. It doesn't look like there is, but there are. Duplicate. Got to move stuff around now because it's a lot of space to take up. Eight Booleans, right? Okay, very simple. We just kind of write them in line. Now, why did I write byte out front? We have to give this constructor a name. There's a reason why we do this later. It'll be clear actually in a minute when we start talking about the numbers. That's how we define it. We call this, when we give a constructor kind of arguments, we're actually giving these as arguments. And I'll show you what this looks like in a second. We call this a, wrong color, a product type. Okay, this is when your constructor, so like true or false, if you also give it some more data. Okay, so it's not just the true and the false anymore. Now it's like a constructor name plus more stuff. So you can say plus more data. Okay, now how do I construct a term in this type? I want to create a byte. How do I do that using our notation? Say just like the 0 byte, a 0, something representing all false. How do I write that? Any ideas? So I can start off, you always write the constructor first, just like true or false. If I want you to say write true or false in our notation, you just write true or false. Simple case, right? Here we write byte. And now we'll write false. I'm gonna use F now just for notation's sake, or save us some time. F, 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 F. Now, how could I write, say, 0, 0, 0, 0, 0, 0, 0, 1? Say that louder.
The last F would just be a true, a T.
Yeah, so the last F becomes a T. Okay, and now you could imagine how you would convert anything now, right? Now, how big is this type? How many things are inside it? Oh, Brian asks, so if there's 8 arguments, are there 8 partial functions? Brian, hold on to that question for about another week, because we'll get to that. Partially applying constructors does a weird thing, so we'll talk about that later. 2 to the 8 says Uller. Is it 2 to the 8? Does that comport with what we know? What is 2 to the 8? Does anyone know? Hopefully not. A little bigger. 256. Hopefully, otherwise I just embarrass myself bad. But should be 256, and we know that a byte represents 256 numbers, right? So there's 256 of them. Or you could say, well, okay, where did we get the 2 to the 8 thing from? Okay, so up in my definition, we can look at, I'm going to copy it. Cool. So how do we get there? We have, well, how many of these are there? How many possible values could that first value take on? 2, right? The next one could take 2. The next one could take 2, on and on and on, 8 times. Now, in order to get our final result, we multiply all those together. Okay, and that will give us 256, or 2 to the 8, because there are 8 2s, right? This is why we call this a product type. Is that clear? It's because when you're going to count them, they become multiplication, the product. Okay, you multiply, right? Anything else I want to cover with that for now? No. What's a limitation of using bytes as numbers? If any of you have done a lot of programming in C, you know the answer to this. Go ahead.
Well, I guess one of them is it's hard to do negatives.
It's hard to do negatives. That's good. A very good point. What's the other problem?
That it only goes up to 2 to the 8.
Yeah, it only goes up to 256. So what happens if I need a number bigger than 256? Yeah, Euler says memory. Like it's just hard. You have a finite amount of numbers you can play with. How do we deal with this problem? Think back to yesterday's intro. Yes.
More bytes.
You could stick on more bytes. That doesn't always work though. It's not a bad answer, but it's not quite like what happens if you keep doing that, right? It fails at some point. You're always kind of finite in size. What if I wanted something that could compute you know, any number, you know, without needing to do any kind of increasing in size. It's hard to do fractions too, Arthur points out. What else could we do? Think back to yesterday's number lecture. We were talking about how numbers came about. What was kind of the pinnacle that we got to? Kind of not as powerful as the real numbers.
I guess you could change the data type that you're using for the byte to make it like base 10.
You could do like a base 10 thing, right? That's really hard to do though, because remember all those patterns we had to learn with addition? Yeah. You have to kind of define out big long functions and tables to do that. Yeah. Not bad on its own, it would work. And you could do the placeholders, you could write floating point arithmetic. We don't quite want to do that though, it's just a little too heavy. Before we had that, we had the tally system, right? We used tally marks. We're going to actually define numbers to be basically tally marks here. We call these the natural numbers. These are actually the piano numbers is what they're called formally. What should I use for headers? I'll use orange for headers from now on. So piano numbers, which is a way of defining the natural numbers, or nat. I don't think I'll call them piano numbers the rest of the semester. Just know that's what the encoding is called. So the nats, right? How do we define this? Can anyone tell me how we get us any new definition started for a new data type? We are going to define a new data type here. Remedial question, should be easy. We first give it a name, and we put that fancy equal definition equal sign. So we'll name it with the shorthand. Sometimes we'll also call it nat. Is defined to be. Okay, so what's somebody give me an idea of some of the natural numbers. Yeah. 0 and up, right? So where could I like start by defining those? If I wanted to list them out. I can start from 0, yeah, I like that. So we have 0. We're gonna actually shorten this to just be Z. I'll usually, I think, use an uppercase Z. And then, okay, so I have another case now. Now, what else is there? So there's definitely 0. We got that on block, right? You know, then there's 1, there's 2, there's 3. That gets redundant, right? Is there a way we could shorten it? Using only 1 symbol? 1 more symbol, to be clear. I want 2 symbols in the system. Instead of using the numerals. Oh, I like it. So Linnea says 0 plus x, which is going to be the form we do use, just in a slightly different notation. So instead, the new symbol is going to be called, it stands in for 1 plus x, and we're going to call it the successor. Okay, so we'll actually write a big S, and we'll call it the successor, or suck. I'll say suck a lot in this class. Just means successor. That's not, I don't think is that how you spell successor? It doesn't look right. I don't know. Anyway, it's a good thing this isn't a spelling class. Now, does successor, does it live on its own? Or does it also need something else with it? If I said something was the successor, then you say successor of what? Well, anytime we call successor, it's going to take another natural number, and it's saying it's the successor to this piece. Okay, that's what you read it as. And so Linnea, this is exactly what you're getting on. It's doing a plus, but we're only ever adding one. Okay. Erase all that. Now, how do we write? Oh, and take my word for it for now. We'll see in a second. This is every number 0 and above can be represented by this. That's not irrational or not a fraction, you know, something like that. It'll represent all of the counting numbers. So how do we write 1? Any ideas? Think about how we wrote byte earlier. That might serve as inspiration. So yeah, Arthur says ZS. That's not it. It's very close though, and Uller comes in with the save. It's going to be SZ. And that's just an ordering thing. So you're right on there, Arthur. So we just write SZ. That's 1. Okay. How do we write 0? Just Z, all right? I'll put that above. How do I write 2? S1, if I spell it all out though, because I don't have the numeral, right? SSZ, right? So I'll usually use, sometimes I'll use parentheses, sometimes I won't for these because it's a little redundant otherwise. SSZ, that's 2. How do I write 3? Yeah, 3 S's, right? Is this boring yet? That's the point. I'm always going to pretty much reduce this stuff to being boring. That's kind of the point. It is supposed to be pedantic, but I think you guys can see where this is going. We can just keep tacking on successors to get any number we want. If you wanted to write 100, it would be 100 S's and a 0, a Z. That's all it would be. So we just took 2 lectures to actually define the numbers. We kind of did it yesterday. This is actually how you formally do it. Okay, so now if we've done this formally, what can we do with it? Well, we can start to define functions with it. There's something else I wanted to hit on first. That's a crutch phrase. If you ever hear me say it, it's because I lost my train of thought. Kind of a big headache to write numbers out this way. At some point, we'll just start using numerals again. It'll just be kind of what we call syntactic sugar. I won't do it for the first few weeks though, so don't expect that.
Can you hear me?
Oh, go ahead.
Yeah, I had a question about like how do we make the translation from all of these successions to what we call 1, 2, and 3?
1, 2, and 3. So I'll try and answer. I think I maybe understood what you're asking. So in order to kind of read these across, we say we have 0 here, and what we have here is the successor or the number after 0. So I'll actually write that as a note. Successor of X is the number after X or X plus 1. Does that answer your question? Maybe? Yes, no, maybe? I'm gonna take that as a yes, hopefully. If not, let it in again and we'll go back to it. So you just count the number of S's, that's your number. If it's just a Z, it's 0. I've just defined the data type. All we have right now is the type. We don't have any fun operations on the numbers. We don't have addition, subtraction, any of the rules for arithmetic, right? How do we define those? Been doing it all class. What do we write? Say to write plus. Or let's say the add to function. So or I just gave it away. We're going to write a function, right? So we're going to write the function that adds 2 to any number. How do we get started with this? How do we always start writing a function? I've asked this question a few times now.
Dots.
Yeah, what do we call that? We give it well, we also give it a name. So we can start with that, add to. We give it a type, right on. What's the type of this function? What should the type be?
The 2-part.
It is 2 parts. So what should I draw though? What symbol are you getting at?
Like the and the natural number symbol.
Oh yeah, so natural number symbol, right? So we have a nat and then
Arrow and then another nat.
arrow and another nat. So in English, it's taking a natural number and returning a natural number. Everyone with me so far? We'll give you a second to write that down. Next, we want to start to define our cases, right? So we define every function as a set of cases. There's always going to be at least one case, except in a very limited circumstances that's very theoretical. Basically, there's a type that has no elements in it, called the void type or the empty type or the null type. Someone mentioned it yesterday, actually, it surprised me. It's the type with nothing in it. It's not super, well, it's mostly not super useful. It's really useful if you're doing theorem improvement, but it's not for most purposes. Here, we're gonna have more than one case. So no, we'll have one case, but more than 0 cases. So I'll start by, oh, did my pen die? My pen died. Oh no. Can I use my finger? I cannot use my finger. Bear with me, guys. Now it's working. We'll see how long this lasts. So we have add to. There's going to be an equals in there for defining it, but what's it take as an argument? Do we need to do any matching here? So when we write these functions, we're always going to kind of start out with the bare form. We can give it, say, an x and just use a variable for now if we don't need to kind of match a pattern to it, right? What goes on the output side? How do I add 2 to a natural number?
The successor x.
Right on. I like it. My pen died again. Sounds like my pen's just dead. See if I can get a trickle out of it for this last problem. Here's what we're going to do instead. I'm going to type. Successor x. This is embarrassing. Let's see if I can move it over. There we go. Successor x. I could put more parens there. That's all we need to write for that function. Very simple function. Because my equipment's failing on me, I'm going to let you guys go a little bit earlier today, especially because we kind of blew through a lot of that today. That was very fast. So that covers everything you'll need for the quiz. We're actually a touch ahead even for tomorrow. So I'm going to have to figure out what we were supposed to cover next week. If there are any questions, I'll hang out for a quick second. I'll have to be good. I'll have to leave a little earlier than I did yesterday, but otherwise I'll hang around for a few minutes, answer questions you guys might have. Otherwise, thank you. Have a good night. Don't forget to take your quiz, please. But otherwise, have a good one, guys. Yeah, thank you.
Thank you.
Yep, have a good one.